Alright, for today we are looking at a situation where two objects are pushed apart by a spring or by an explosion or something where we have our two objects initially at rest and then some sudden force is going to cause them to move apart from each other. Now, when I was in high school, we used to do this with a firecracker. We'd have two carts on an air track right next to each other, and you put a firecracker in the middle and light the firecracker, and the explosion drove them apart. We don't live in a time anymore where that would be an acceptable thing to do at school, but the spring idea certainly would be fine. And it's an interesting problem and a good time to review our general problem-solving process. Some of these are not going to be real obvious what the general process is to begin with, so we kind of have to think backward. So in this one, we've got our starting state where we have our two objects here at rest, and then this spring is compressed in between them, and I've got that labeled with a length right now of 0.25 meters, so it's 0.25 meters from here to here. And then in the final state, we have these two objects now moving apart from each other. We know how fast this one's moving, but not how fast this one is. And we can see that this spring has stretched out a little bit. It's just lying on the ground there, and now has a length of 0.50 meters. So we can tell that the resting length, or the unstretched, uncompressed length for that is 0.50 meters. When it was compressed, it had a length of 0.25 meters, so we can get the compression distance that way. This problem asks us to find K, the spring constant for that spring. Now, with the information that we're given here, like I said, it's not an obvious process. So we're always going to start, when we're trying to figure out a way to go about this, we'll start with our end result. We need to get to K, and then we'll kind of work our way backward from there. So we think about what equations K appears in, what relationships we have for K. And really there's two of them. So K appears in, force from a spring is equal to negative Kx, and it appears in the equation Us, the spring potential energy, is equal to 1/2 Kx squared. And so we start to examine these and think, what information would we have that works best with this? So K is what we're looking for. We won't know that in either equation. X we can figure out based on the length when it was stretched or not stretched and when it was compressed. And then we need to get some information about either the force for that spring or the amount of energy stored there. Now the force for that spring, well, we might be able to do something with that if we could get acceleration for either of these blocks while they were being pushed by that spring, but we don't really have any information about time, so we don't know how long it took this one to get to 4 meters per second. We don't know how fast this one is going. We might be able to get there, but the time issue, that's a problem for us. So let's put this one on hold. Maybe we can come back to it. In this one, we'd need to know the spring energy. Now, spring energy, we have this relationship defined, which we can't do yet since we don't know K, of course. So we need to think about other ways we might be able to find out how much spring energy it has. Well, the amount of spring energy, or elastic potential energy, that was stored at this moment in time has to be equal to, so since we had our objects both at rest here, and we had that spring compressed, and we didn't have any change in height for a gravitational potential energy, the spring energy at this moment is the total energy. That's all the energy in this two object and one spring system. And then over here we have our two objects moving in opposite directions. Our spring is no longer stretched, so that spring energy we had here has been changed into kinetic energy split between our two objects. So we can work with that then. We know that the total energy initial has to be equal to the total energy final. And in this case, the energy initial is going to be equal to spring energy energy final, and that'd be initial. Energy final is going to be kinetic energy. And so we need a way to figure out what the kinetic energy is at this moment. Now, this object, we can figure out pretty easily the kinetic energy there. We just do 1/2 times the mass times the velocity squared. But this one, we don't have a velocity. Okay, so we need to work backward a little bit further. We need some way to figure out velocity at this moment. Well, velocity appears in a number of different equations, but when we have both an initial and a final state like this with two separate objects that are changing how they move, that kind of screams momentum. Look at momentum for this situation. We know that momentum has to be conserved for any closed system. We've got our three objects here, if we include the spring there. Initially we had a total momentum of 0. In the final state, the spring is just sitting at rest on the ground there, so no momentum there. This one has momentum to the left, this one has momentum to the right, so I know that this has to have the same momentum to the right as this one does to the left. So I can use that fact to solve for velocity. Okay, so we're going to work back even a little bit further and do a conservation of momentum. So initially we had both objects at rest, all three objects at rest here. So our initial momentum is just 0. And in the final state we've got, let's see, our 1 kilogram mass going to the left at 4 meters per second. So mass times velocity, 1 kilogram times negative 4 meters per second. I'll just call them, whoops, that's not squared. Call my leftward direction negative. And then in the right, for this other object, we've got 2 kilometers times some velocity, and that's going to end up being to the right. I said kilometers, but I meant kilograms there. Okay, so now we can solve this. We got here, we'll have negative 4 kilogram meters per second. I'll add that to both sides. So 4 kilogram meters per second is equal to 2 kilograms times v. So that's going to mean that when I divide by 2, I get 2 meters per second is equal to velocity for this second block. So I'll fill that in. 2 meters per second. Alright, now I know velocity for each of these, so I can figure out what the kinetic energy was. So I know that the elastic potential energy is going to equal, initial, is going to equal the total kinetic energy final. And make sure that's a capital K there. So we've got 1/2 kx squared, initial, is equal to 1/2 m, I'll call that m1, v1 squared, plus 1/2 m2, v2 squared. So the kinetic energy for both objects moving at the very end. So now I'll plug in what I can, 1/2 times k times this, x is the stretch distance or compression distance. So we started out at 0.25 meters. When it was relaxed at the end, it was 0.50 meters. So we can tell that it was compressed by a distance of 0.25. That'll be equal to 1/2 times the mass of the first object, which was 1 kilogram. Times its velocity, which was 4 meters per second, and that gets squared, plus 1/2 times the mass of the second one was 2 kilograms, times its velocity was 2 meters per second, oops, and that gets squared. And then on the left side, we're going to have 0.25 squared, so that's 1/8, and then times 1/2 is 1/16. So k times, let's just write that as 1/16 meters, meters squared rather. It's going to be equal to, let's see, 4 squared is 16 divided by 2, so that's 8 kilogram meters squared per second squared, plus 2 squared is 4 times 2 is 8 divided by 2 is 4 kilogram meters squared per second squared. Oh, and I'm out of space, so let's move this over here. I'm going to multiply both sides by 16 to get k. So 8 plus 4 is 12, and then k is going to be 16 times 12, which is 192. And the units on that are going to be, let's see, we'll have kilogram meters squared per second squared divided by meters squared. So that's just going to be kilograms per second squared, or another unit for that is newtons times meters, or sorry, newtons per meter. Newtons are kilogram meters per second squared, so newtons divided by meters are kilograms per second squared. Same units there.